Good morning, afternoon, or evening, everybody. Welcome to the ABoVE Data Management Best Practices webinar. This is your host, Jennifer Brennan. While everybody is logging in here, you will notice that we've got two optional polls, and you'll find those located on the lower left-hand and middle portion of your page. And we very much appreciate your feedback on these polls. They help us to continually improve our webinar series. I do have 2 p.m. Eastern Daylight Savings Time, so right now we're going to go ahead and get started. First, what I'd like to do is go over some housekeeping items related to this webinar. To ensure best audio experience, this conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod located on the lower right-hand side of your screen, and this works like a chat. This webinar will be recorded and is being posted both to our online Adobe Connect webinar catalog as well as to our NASA Earthdata YouTube channel within a few days of completion. And I do plan to provide that URL to all of you at the end. All presentation files will also be available for download at the end of the webinar. As far as timing is concerned, this webinar will be 1 hour long. We've allocated 45 minutes to the presentation with an additional 15 minutes for the question and answer period. After our speakers have finished their presentations, we will then move to the final set of polling questions, and then from there, we'll transition directly to the Q&A period. You will have an opportunity to ask your questions throughout all portions of the webinar by using the Q&A pod. This works like a chat. Again, questions will not be answered using the raising hand function. It has been disabled. And just one final note, depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. for those of you who may wish to stay on the line. And before I go over the agenda, what I'd like to do is introduce today's 3 speakers. Our first speaker is Dr. Allison Boyer, who is the Chief Scientist for the NASA Oak Ridge National Laboratory Distributed Active Archive Center, or ORNL DAC. Our second speaker is Dr. Yashing Wei. He is a Geospatial Information Scientist at NASA Oak Ridge DAC. And finally, our last speaker is Suresh Vanand, who is the NASA Oak Ridge DAC Manager. So let's move next to the agenda, and I'll pull this up here for everybody. Okay, hopefully everybody can see that just fine. I might have to scroll a little bit here. During today's webinar, Dr. Boyer will kick it off by discussing why data management is important, and then from there we will transition to a more in-depth look at how data management principles. And finally, the remaining portion of the webinar will focus on how to manage your data throughout the course of a project. We will discuss NASA ABoVE specific guidelines and then finish the webinar with information on how to submit data to NASA Oak Ridge DAC. Excuse me. With that, it is my pleasure to introduce our first speaker today, Dr. Allison Boyer.
Thank you, Jennifer, and welcome to the ABoVE Data Management Best Practices webinar. I'm Allison Boyer, and I'd just like to take a moment to introduce you to the ORNL DAC. The Oak Ridge National Laboratory houses the Distributed Active Archive Center that supports NASA's Carbon Cycle and Ecosystems Focus Area and archives data from the Terrestrial Ecology Program at NASA. We have over 1,000 data sets currently in our archive, mainly falling into 4 different categories. Those are the field campaign data, including data from programs like ABoVE. We also archive model code. We archive land validation data sets that are used to validate satellites like MODIS. And we have a large collection of regional and global data, both model input data as well as model output, and other data sets that are of general importance to the NASA terrestrial ecology community. Our website is dac.ornl.gov. You can see that on the right-hand side, and I encourage you to browse our collections and see if there might be data that's of interest to you. The goal of today's workshop is to provide you all with some data management practices that you could perform during the course of ABoVE projects. and this will improve both the usability and the lifetime of these data sets. Now, this webinar is focused on ABoVE, which is the Arctic-Boreal Vulnerability Experiment funded by NASA's TE program, and this project is taking place from 2016 to 2021 in Alaska and Western Canada. However, many of you may not be involved with ABoVE, and I hope that this webinar will be of general interest for data management and operation of ORNL DAC in general. So why should you bother following good data management practices? Well, the benefits are both short-term and long-term. In the short term, you can see benefits to yourself as a researcher because you can spend less time munging your data, organizing it, and remembering what your data represent, and more time just doing the research and analyses that you need to do. In addition, your collaborators can more easily understand and use the data files that you share with them. In the long term, after your project is over, data archival will pay back dividends to the scientific community and to you as a researcher, because scientists outside your project will be able to find, understand, and use your data, and you will get credit for archiving your data products and any time that someone uses them in another paper. The funding agencies also protect their investment in your data by ensuring that it's available for continued research after your specific project has ended. So today we're going to go over 10 principles of data management that'll be of use to you in your research. Those 10 principles are listed here. First of all, you should define the contents of your data files and define the variables. This is part of using consistent data organization. Number 4 is to use stable file formats. You want to assign those files descriptive file names as well. And in doing so, you can also preserve the processing information that you use to analyze and arrive at those particular data files. Number 7 is to perform basic quality assurance. You want to also provide documentation, protect your data, and finally preserve your data. Now we'll delve into these 10 topics in a lot more detail. And to help with that explanation, I'll turn it over now to my colleague, Yashing Wei.
Thanks, Allison. Hi, everyone. This is Yashing Wei. So let me talk about a few fundamental best practices for data management. And I'll start with defining contents of your data. And this can start really early when you are planning for a project. And content flows from science plan and it is informed from requirements of potential final archive. And you may want to keep a set of similar measurements together in one file, for example, measurements done by the same investigator using the same method, collected during the same time period or by the same instrument. There is no hard and fast rules about content of each file, but you may want to avoid lumping everything together into huge files or spread too thin and create too many small files. And second, define the variables well. This is one step forward to make your data contents more concrete. For example, you want to measure temperature or soil moisture variables and choose the units and format for each variable. Explain the format in the metadata and use that format consistently throughout your files. And assign commonly accepted names and units to variables. And you may want to check with ISO 8601 to find standard ways of dates and time representation. The International System of Units and UD units provide you guidance on choosing data data units. And the climate and forecast, or CF, maintains a list of community-contributed standard names. And the variables you measure may already defined in the CF standard name list. And one important thing I want to mention here is the missing value. Use a value or a code like -9999 to represent gaps of time series measurements or areas your data don't cover spatially. And variable names are very important, especially for others not familiar with your research and needs to use your data in the future. And always use unambiguous and interoperable variable names. And build a table that defines the short name and full name pairs for variables in your project. And the full names provide precise definitions, and short names can be used consistently and conveniently in your project. And on the ABoVE website, you can find a list of potential measurements to be measured by ABoVE. And that can be a good source for you to define variables. And the direct link to the ABoVE potential measurements is provided on this slide. So on this slide, I want to show you a good example for variable definition. And this was a study about woody vegetation in Africa, a Safari 2000 project. And this data set is archived at the ORNL DAC. And as you can see, this data set provides a table that defines the short name, the description, and units for each variable. And of course, the description for those variables could be better by using standard names, for example, those defined in the CF standard name list. And it's also a good practice to define a site table for your project, like this Safari 2000 project did. And this table lists all the sites at which measurements were made, along with standard names and codes for the sites, coordinates, and elevation information, those site characteristics. So the greatest benefit for doing this is consistency. Imagine those situations like different people call the same site differently or use different latitude and longitude coordinates, and that can be really messy. And I want to point you to the ABoVE sites and measurements planning tool. And the direct link to that tool is provided here, but you can also find it on the ABoVE website. And with this tool, you can find and visualize the sites and that ABoVE measurements conducted in the past, currently, or in the future. You may want to pick the same locations as other investigators choose to make measurements more integrated and comparable. And of course, if you pick an existing site, do not assign it a different name that only you know. And this tool is really a good platform for ABoVE investigators and to coordinate and collaborate. So the third good practice I'm going to talk about is to use consistent data organization. And on this slide, it gives two examples of organizing measurements in tabular format. It can be the wide format. Each row in a file represents a complete record, and the columns represent all the variables that make up the record, or the long format shown on the right side. The variable name, value, and units are placed in individual rows. But no matter which way you choose, always do it consistently. And a common bad practice I want to mention here on this slide is to leverage advanced features of some commercial software, such as Excel, to organize your data. For example, some rows are highlighted with a special color, and multiple sheets are included in one Excel file, and plots and figures are embedded. And these features of Excel can be nice for you if you just want to conduct analysis or presentation during the course of the project, but are not good for organizing data to be used in the future for long-term data preservation. And we will talk about why in the next section. And use a clean and simple comma-separated value, or CSV, format to organize tabular data, like this above burn severity data archived at the ORNL DAC did. And one date file in this project was an inventory of wildfires happened in the Northwest Territories, Canada in 2015. And notice on this tabular data that consistent side codes were used. And you also notice that some rows on the most right column, -9999, was used for missing data. So this is really a good example of organizing data in tabular format, and this is an above example. So the next best practice I want to talk about is to use stable file formats, and this is very important for long-term data preservation. Avoid proprietary formats when you choose to archive data. They may not be readable in the future. For example, the Excel format. In 10 years later, things can change, and Excel may be difficult to read. And this BBC News told a nice story about that. And old digital file formats can be a ticking time bomb. So what formats can be considered as good formats? They shall be simple, open, and commonly used by the communities. For example, GeoTIFF, NetSDF, especially those with CF convention, and HDF, and also ASCII, a good format for representing raster data or graded data. And shapefiles and pure ASCII or CSV can be good for representing vector data files. So the next best practice is to assign descriptive file names. And those good and descriptive file names shall be unique and reflect their contents, and use ASCII characters and avoid those special characters. And on this slide, you see that mydata.xls is really a bad name because you can see nothing about its contents by just looking at the file name. A better name here contains name of the project, a site name, what was measured, and when. And for model outputs, if you're conducting modeling research, you may want to include model name, simulation code, version number, variable name, spatial information, temporal information, and your model output file names, such as those names used by the North American Carbon program and the model intercomparison project. So these are some good file name examples. And once you have all the files created, organize them logically in a hierarchical directory structure. For example, on this slide, you see that if you conducted biodiversity study about lake and grassland, they can be organized into two separate subdirectories. And data from experiments and field work in each region can then be further organized under each category. So preserving processing information, this is very important. Always preserve all your processing information. And to preserve your data and its integrity, save a read-only copy of your raw data files with no transformations, interpolation, or analysis performed on top of that raw data file. You can leverage your operating systems to make those directories or files read-only, so you won't be able to delete them by mistake. And use a scripted language such as R, SAS, or MATLAB to process data in a separate file and located in a separate directory. The codes you have written are an excellent record of data processing, and they can also easily be and quickly be revised and rerun in the event of data loss or request for edits, and have the added benefit of allowing a future worker to follow up or reproduce your processing and try to link your processing codes with the data that the codes runs on. And keep in mind that while graphical user interface-based programs are easy on the front end, they do not keep a record of changes to your data and make reproducing results difficult. In this example on this screen, an R script to call is made on the dataset to plot the data and perform a log transform. This way, changes are not retained in the original raw data file. So the next practice is to perform basic quality assurance. For tabular data, ensure that data are delimited and lined up in proper columns, and check that there's no missing value or blank cells for key variables. Here we mean missing value is really values are missing. That means no values were provided. Try to avoid that. Use a negative 999, for example, to represent measurements that you didn't make. And scan for impossible and anonymous values, and perform and review statistical summaries, and map location data, the data with coordinates information and access errors. Of course, there's no better quality assurance than to really analyze your data. So next screen, I'm going to show you an example of utilizing mapping tools to quality check coordinates of site measurements. So on this screen, you notice there are two sites. One is actually an Illinois site. It's mapped somewhere in the Asia. And there's another Brazil site located right in the ocean. So with this mapping capability, you can easily find there are problems with those two sites. The coordinates are wrong. And it turns out the latitude and longitude coordinates of those two sites miss the negative sign. So now let me turn back to my colleague Allison, and she will continue with some practices about documentation, data protection, and preservation. Thanks.
Thank you, Yixing. So the number 8 on our list of the 10 best practices are to provide documentation and metadata. Now, some people may be aware of metadata as being an XML format, a very detailed document that has to be set up in a certain way. But in general, metadata just refers to information about your data. And sometimes I refer to this as documentation about the data set. In this metadata, you want to include the what, why, who, when, where, and how of your data. What is described, why was the data created, who produced it, when and where were the data collected, importantly with respect to spatial resolution, and how was each variable measured. It's also important to assess the uncertainty or accuracy of the data by recording information about how reliable are the data and what problems might remain. What assumptions were used to create the data set. Finally, your documentation might include some information about your usage policy and expectations in terms of data sharing. How could someone get a copy of this data set? You also would like to provide any references to publications that have already used this data so that potential future users could see an example of how it was being used. This documentation would not necessarily have to be an XML metadata format, but before sharing your data, you might prepare a README file just in text format that addressed each of these points. And that would go a long way toward ensuring the correct and accurate reuse of your data set. Number 9 is to protect your data. You need to create backup copies and update them often. Now, we hear about this all the time, but it doesn't really hit home until you actually lose data, like I have, and then you remember to always have 3 copies of every vital data set. Ideally, you would have your original data set maybe on your work computer. Then you might have one on-site backup, such as an external hard drive. In addition, it's good practice to have one off-site backup as well. This could be on a server at another institution, or it could be something cloud-based like Dropbox or Google Drive that would not necessarily go down if you had a local natural disaster. And it's important to periodically test these backups and make sure that you could restore your data if you needed to. Now, the hard drive manufacturer, LaCie, estimates that up to 1/3 of data loss is due to events beyond your control, things like natural disasters, software corruption, or sometimes computer viruses or hackers. But that 31% leaves a lot of room for improvement in just preventing user error or human error. So besides backing up copies, it's important to make sure that everyone realizes and is aware of the need to prevent human error in losing data. Finally, the last point in this data management top 10 is to preserve your data. After you've gone to all the work to collect the data and analyze it and organize it, you want to preserve that work just in the same way that you would preserve your published papers that result from the research project. So what should you preserve? Well, you definitely want to preserve those well-structured data files that have all the variables, units, and values that you've carefully defined. If you prepare a README file or a metadata record describing the data, you should definitely preserve that along with the data files. But you can also preserve additional information that provides context about the data. These might be materials from your project website or a wiki. They might be files describing your project data collection protocols or your field sites, including a field journal if you took one, or photographs of the sampling regime or the field setup. Finally, you want to preserve publications that were based on the data set as well. Now, if you preserve this data, where should it be archived? This should be part of your project planning from the very beginning. If you wrote a data management plan as part of your proposal, then you should have proposed a data center to archive the data at that stage. Now, during the project, you could contact this archiver data center and find out what their requirements are. They might have expected some additional data management steps during the course of your project. Now, for ABoVE specifically, ORNL DAC is designated as the archive for all the ABoVE data. But data that comes out of ABoVE might also be sent to other repositories in addition, like LTER, ACADIS, or movebank.org. And each different archive might have different types of requirements. This is something that you should just be aware of as an investigator looking to archive your data long term. So this gives you an overview of the 10 best practices for data management. There's a lot more information on that topic available at the ORNL DAC website. Now my colleague Suresh will talk you through a little bit about data management at the project level.
Thank you very much, Alison. So my name is Suresh London, and my colleagues Yashing and Alison went through these best practices of data management at a data set level. And my goal is to talk about data management at a project level. So what are the aspects of data management that you should consider as you begin your project? ABoVE is a very collaborative project where interaction and communication amongst many different research groups is critical. And this is just not unique for ABoVE. I think several projects which have data collections are working with many different investigators, many different teams in assembling that information together. So here are 6 principles to begin with in terms of effective data management at the project level. So the very first thing is to define the data workflow. So as you begin your project, you have a clear idea in terms of what measurement or variable you are going to be capturing on the ground. So that workflow of data collection to archive needs to be mapped out. As the data flow is defined, the communication standards and metadata needs has to be made. So before you communicate, first you need to assign these standards and metadata. And it is always better to define those standards early on within those projects. So everybody on the measurements team and the data collection team understand what standards and metadata has to be captured and how they have to be captured. We already talked about some ABoVE specific standards and metadata considerations, and you can always refer them for this particular use case. And then as you do those measurements, it is critical to have a data quality criteria defined. So the measurements may be from an acceptable range, and the quality information has to be represented and documented as well. So this is actually quite critical when you have many different teams making measurements in different locations, and having an established data quality criteria documented and communicated amongst the team would really ensure that the data can be integrated and used together. In terms of defining the workflow and the data and the metadata process, this has to be documented regularly. And in some ways, it is better to establish that process early on in terms of defining as to when the documentation needs to be collected, what format, and how they have to be stored should be discussed at the project level. For large projects, if you have multiple teams working on different parameters and measurements, you may consider identifying a data steward. So this could be a person or a team who could be in charge of making sure that the entire team is following all the best practices of data management. So this actually comes in quite handy when you have a long-term project and you have measurements that have to be collected over multiple years or perhaps even decades. So this ensures that there is an identified personnel and a process in terms of maintaining and documenting your data. Allison already mentioned about the data use and the submission policy. So at the project level, you may think about internally as to when a data has to be made available. So sometimes it may be obvious that within the team as to when the data is going to be made available, but having it documented and discussed within the planning phases of the project would be helpful. And then during that phase, you may also think about how this data is going to be published to the public. Would there be any embargo period because of the sensitivity of the data that's collected, and all those things have to be discussed within the team and also with the sponsor and with the archive as well. So here are some 6 principles, and like Allison said, there's far more details about each one of these individual elements on the ORNL DAC data management website. So now I want to walk you through an example of this data management. So here's a wheel of information which talks about all the different aspects of data management at the project level. So what we were going to be doing today is to just highlight 3 of those elements as examples. So from planning to considering the data, to standards, data quality, authorship, steward, and so forth. There are many different elements which forms the life cycle of data management at the project level. So in this particular example, we're going to take this ABoVE Burns Viarity data set. This is a recently archived data at the Oak Ridge DAC. And the example that's going to be shown over here is how would a team approach data management for this particular data set, right? So as I mentioned, this particular project is going to capture data of the post-fire environment in the Arctic-Boreal region. So that is being defined, that's the plan, and the collection of this data is going to happen through field surveys. So the method of data collection is also documented and defined as well. So one of the criteria that this team might use is to say, okay, we're going to reserve 10% of the budget for effective data management, right? So in other ways, another way of thinking about this is 10% of an individual's time has to be spent on data management. Like I mentioned before, if you have a fairly large project, you may consider having a data steward, but the data stewardship has to happen at the individual team members level as well. And then within the planning, the spatial region of how the data has to be collected is defined as well. And with ABoVE, there is a specific ABoVE domain area and grading system that has to be followed. We'll talk about that a little bit later, but that definition of the spatial region is also defined as well. The file format, it's better to define the structure of those file formats, not only deciding on what file format it is, but the structure of that file format needs to be defined and communicated as well. We talked about the data submission guidelines. In this particular example, the team has decided to send this data over to the Michigan Technical Research Institute. And again, these are hypothetical cases. We're really not sure as to how the team approached it, but we're wanting to use an example of how to approach data management from a planning phase. So moving on, in terms of data, the project has 3 deliverables in terms of data. The first one is creating a land cover classification map. The second is creating the fire progression maps. And the third is the vegetation community biophysical data. So here are 3 outputs of data that's going to be collected as part of this project. The table at the center is not quite visible, but the idea is that in terms of biophysical data, all the parameters and the description about those are defined and communicated early on. So this is something that you need to do not as an afterthought, not at the end of the project, but before the first data collection happens. And then in terms of standards, we already talked about CSV as a good format for tabular data. These are comma-separated values. You avoid the proprietary nature of software such as Excel. I know you missed some functionalities, but this would ensure readability across different teams, and also make sure that those data sets could be integrated into multiple softwares as well. If you're considering GIS data, GeoTIFF is a good format. In this case, the land cover maps could be prepared in a GeoTIFF format. And then any pictures of the site measurements of the biophysical data could be stored in a JPEG format with georeferencing information. The coordinates of the site information has to be stored with at least 6 significant digits. We've seen several examples of data that have been archived, where the site information lacks the precision that's critical for identifying the variables and pinpointing them to the ground. So just having 1 or 2 significant digits would really not allow us to be able to go in and say this measurement was taken at this particular point on the ground. And then along with the coordinates, the projection information has to be defined as well. And then we already talked about uploading these data sets. So this team basically decided, okay, we want to have 2 days, upload the data within 2 days of the field work. And as we mentioned earlier, backing up the data is very, very critical, because you cannot, the amount of labor and time that's invested in making these data collections, you certainly do not want to lose all that information as well. And again, documentation should be defined and established by the project leader to say that the documentation has to be done as and when the data is uploaded into the system. So there are several other elements of data management that has to be considered, but we just wanted to give you a quick example using the planning stages, the standards, and data structures to define those elements of project-level data management. So now we want to give you some specific information related to ABoVE. ABoVE investigators have a defined study domain in which they're making those measurements. Those locations, there is a convention by which those site measurements have to be structured. There's more information about this available on the ABoVE website. The measurements have to be located within the study domain of ABoVE, and the grid location of those measurements have to be documented as well. So this is actually quite important to basically interlink the data and combine data across many different instrument schemes as well. The measurements variables, Yashing mentioned that the ABoVE team has a set of defined variables, and do take a look at those as you start your data collection exercises. The ABoVE team has defined a projection, a suggested projection. Actually, this is the projection that the team is going to follow, the Albers conical equal area projection. So if you're preparing GIS data sets, make sure that your data set is prepared in this particular projection. So all these are defined in the ABoVE implementation plan, and you can read about that and get in touch with the CCNE office for further information as well. But the main message here is having this standardized structure will allow interlinking and synthesis of the data to answer bigger science questions. So that's really the biggest motive for making this standardized. So now, as an ABoVE investigator, we want to talk through the data flow from you as a data collector to how it ends up into the Oak Ridge DAC. So you've made some measurements on the ground. You've collected all these measurements, and you might be using the ABoVE Science Cloud to run your synthesis. So the ABoVE Science Cloud is a shared computational infrastructure. You, as ABoVE science investigators, you have access to the Science Cloud, and that could be used for running any large-scale analysis platforms that could not be done on the desktop. Now, so there's a back and forth that might happen between you and the Science Cloud, but any data sets, you may have data sets that really doesn't qualify for the Science Cloud. These are not big enough synthesis. It's data collection. You've run your analysis. Those finalized data sets should be sent over to the Oak Ridge DAC for permanent long-term archive. The Oak Ridge DAC is part of the EOS-DIS data systems, and that data will be made available to the larger group of community. And if that data set is going to be useful in the context of the Science Cloud for further analysis, we can make that data set available in the Science Cloud. We have 2-3 data sets already available in the Science Cloud, and so this can actually form a loop in terms of how data could be used within the ABoVE Science Cloud and into the permanent archive. But I want to reiterate the fact that Oak Ridge DAC is the permanent archive for the ABoVE, and the data should be made available. The finalized data should be made available into the archive. So now, how do you submit the data into the Oak Ridge DAC? So the very first step is you can go onto the Oak Ridge DAC website. There is a Submit Data button at the very top of the website, or you can link directly to the Initiate Submission form. So you expressed an interest in submitting the data over to us, and if this data set qualifies to be archived at the Oak Ridge DAC, then we would initiate a data submission process, where you would upload documentations, upload any processing scripts, upload any of the metadata and the data sets into the system, and then we would do the data curation and publish those data sets. Here's a quick overview in terms of how data is published at the Oak Ridge DAC. But I wanted to say what is the value of the Oak Ridge DAC in this curation process. The very first thing is we go through a detailed quality review checklist. All these best practices that we've talked about, we apply those into those data files to make sure that those data are readable by a user 20 years into the future. So we go through a detailed data quality checklist, and preparing documentations in a standardized format helps any user who's unfamiliar with those data sets and use them as well. And we publish those data sets for the broader user community. So why do you want to publish? Allison talked about the benefits of publishing these data sets, but I want to reiterate this because this is a very critical piece of information. You as data producers spend a lot of time preparing these data sets. So by publishing these data sets, you get the credit through data citations and digital object identifiers that you can put into your CV And a lot of universities and educational institutions are also recognizing the importance of data publication as well. Your data, if it's published, could be shared of a larger synthesis activity, and that's quite critical for a project like ABoVE. You can, as a data creator, measure the impact of your data. Right? Your data is some ways a proxy for your research. It's an outcome of your research. You can measure the impact of that through citation statistics and download statistics. And leveraging an archive and a data publication system such as the Oak Ridge DAC, you can make use of visualization tools, subsetting capabilities, access through web services, and really improve the usability of those data sets. So here are different, you can so-called carrots to publishing data sets. But there is a requirement, in terms of publishing these data sets. There is a mandate to make sure that the data, which is funded by the government, by the U.S. government, should be made available to the public because it's federally funded scientific research. So here are processes by which you can make that happen. And now I would like to turn this over to Jennifer. Thank you.
All right, thank you, Suresh. Thanks, everybody. So what we'll do next is we will move to the final set of polling questions, and we will give these questions just a couple of minutes or so, and then from there we'll move to the Q&A period. All right. And don't worry if you can't see the Q&A pod right now. There was a comment that I will share with you when we move to the Q&A. That's a persistent feature. So just as soon as we move to, from the polling questions to the Q&A, you'll see them again. And we did have a question early on and then a comment that I'd like to share with you. All right, thanks everybody. Okay, everybody, we're going to give these just a few more seconds here, and then we'll move directly to the Q&A. Okay, everybody, with that, let's move to the Q&A period. And I do want to share the comment is from Dr. Peter Griffiths, and his comment was, I'd like to say that the ORNL DAC is the designated archive for most ABoVE data. We have several examples where some data may permanently reside elsewhere, for example, where original observations in ABoVE are done by other agencies with their own requirements for archive. In those cases, what's archived at the ORNL DAC may be the derived collaborative data products. All right. And with that, I'd like to jump to our first question, which was asked quite early on here. And the question is, What is the purpose of the negative 9999 instead of a null value?
Thanks, Jennifer. That's really a good question. I want to address that. So the purpose of using negative 9999, for example, instead of null value, is to increase consistency and interoperability. For example, negative 9999 is a number. No matter it resides in a binary data file or a text data file, no matter which programming language or tool you're using to read that data, it's always interpreted as negative 9999, a number. But for null value, there's no universal consistent way of representing that. For example, if you create a binary file, for example, NetSDF, and using a language like MATLAB, and you put null value there, it's represented as a binary NaN. But if a null value is represented in a text format, it's probably something like not available or not a number. There's just no universal way of representing a null value. So I can think of two situations that the null value may cause problem. The first situation can be if you create the file and put a null value there. For example, if you are using MATLAB to create that data file, and someone else is going to use your data file, but they are not using MATLAB to read your data. They may use like Fortran or C or some other tool, and their tools may interpret the null value differently from what you put there. So that's the first situation. That may cause problem. The second situation can be if you create a file and that file may be converted to some other format in the future, and the null value may be changed. The representing of null value may be changed during the format conversion, and that may cause issues in the future. So there are a lot of problems with using null value. So we really recommend that you use a true number and document that this particular number represents missing value. That increase interoperability and consistency, and it's a good practice.
Okay, thank you, Yashing. The next question is, how do you feel about IPython or Jupyter notebooks?
So I'll address that question too. We really recommend that. We have leveraged IPython and Jupyter notebooks to build some tutorials to train our data users to use our data products and also the data access web services that ORNL DAC hosts. So that's a really good platform, a good tool, and we recommend that. So please go ahead to try that, and that's very helpful. And it's also good for, especially if you want to present something over the web and allow users to try and change some parameters and rerun your code. So that's a really good platform.
Okay, thank you, Yashing. Our next question.
Alison also wants to add something.
Yeah, just on the topic of IPython or Jupyter notebooks, from the perspective of archiving the data, even if you don't use a specific IPython notebook, even if you just provided a script that would read your data files and do some basic analysis, if you would like to provide that type of script alongside your data files, the ORNL DAC is definitely able to archive those scripts. And we can archive your entire IPython notebook along with the data files themselves. So we consider those types of scripts as additional documentation or context for the data.
Okay, thank you, Allison. And thank you, Yashing. The next question is, when we are distributing code, are legal statements okay or needed? For example, disclaimers, distribution, modification notices. Presumably, copyright does not apply if code was developed using NASA funds.
Well, that's a good question. The ORNL DAC, being a NASA archive, has no, it does not attach any usage statement or legal copyright notice to the data. It's just public domain data being produced by NASA funds. So if it was developed with NASA funds, then I don't think that we need to attach any sort of statement. But that's just my perspective from the DAC. If the code originated from some other source and some other funding line, then maybe you would need to check with that funding agency. But in general, all the code or data that's released through ORNL DAC would be available with no licensing requirements whatsoever.
Hey, Allison, can I add something to that?
Oh, Peter, yeah, go right ahead.
I *6'd myself into the audio. This could be a subject for greater detail in a Science Cloud webinar, but we do have a few special categories of copyrighted data that are possible. For instance, Canadian Space Agency, RadarSat, data from the Japanese Space Agency with ALOS Pulsar, and from the Digital Globe high-resolution commercial imagery from that we get through the National Geospatial Intelligence Agency. There are specific requirements for acknowledgement and in some cases for a copyright being on the data product in some of those cases. So there's special cases that don't warrant going into in this, but they will exist, and so we should anticipate a few cases like that.
Thanks for enlightening, Peter. We should take it offline, but I'm thinking mostly of investigator generated data sets in this case.
Yep. Yeah, so observational data, that they're doing in the field, it's very clear unless there's a human, there's a personally identifiable information and some sort of demographic, there are restrictions to that. But some of the data sets that people produce from these copyrighted sources still retain the copyright. So even if it's an investigator-generated data product, if they are drawing on a copyrighted source, then there are cases where the copyright follows to the product. But we'll work, individually with people, and particularly with the Digital Globe imagery, because it's a whole presentation into itself.
Okay, thank you. In the spirit of time here, I just want to make sure we can get to all of our questions.
Yeah. Let me throw one other thing in though on the for ABoVE data where there are restrictions, and it's in our implementation plan and the data policy. The one other category that we shouldn't neglect is traditional knowledge and indigenous knowledge. So ABoVE investigators are working with local people and Aboriginal peoples, and there are very particular ways that for recognition and managing that data that we'll have to attend to. And please go ahead.
Okay, great, thank you. So the next question is, okay. Thanks for speaking to the importance of reproducible research. I like IPIPE, so it's more of a combination, a comment and question. RS Studio and provides a robust implementation of a similar protocol called NIT-R. Does NASA have a repo or clearinghouse for practitioner work based on these reproducible platforms?
Thanks, Jennifer. This is Yashing. I know that NASA ESDIS has set up some test Jupyter Hub platform, but that's internal access only. I'm not aware of any publicly available platforms for Jupyter Hub or NeatR. But there are some these kind of platforms available maybe outside of NASA. But I think this is really a good question. Maybe for the above team to think about whether it's needed to set up such a platform so that above investigators can leverage and collaborate throughout this platform.
Okay, thank you, Yashing. I am scanning the Q&A pod to see if there are additional questions. Does anybody have any additional questions? Okay, here's our next question. How are you collecting the native information? Is that by video?
Well, we haven't received any native information yet, but so the investigators who are proposing to do that work would be collecting it in the best means that they would standardize. And at ORNL DAC, we'll simply take that data in as we would any other data set, perhaps placing restrictions on it if necessary. So I think that you'd have to redirect that question toward the investigators who are actually doing that research.
Okay, thank you, Allison. And while we're waiting for any additional questions, I just wanted to point out in the lower right-hand corner of your screen, if you were to highlight, we've got both the agenda as well as today's presentation uploaded to the file sharing pod. And so if you were to highlight either one of those files, you will be prompted to download the file. And let's see here if we have any further questions. Are there any additional questions? We'll give it like a minute or so here. If there are no further questions, what we will do is we will log off from the telecon portion of this webinar. However, I generally keep the virtual meeting space open an additional 10 minutes for those of you who may wish to download the files, or if you think of a question that you'd like to ask, we can certainly forward those questions to the speakers today. You're quite welcome, Jennifer. Any additional questions? All right. Give it just a couple more seconds here. Okay, here is actually a question. Will HDF be required for the remote sensing data?
I think HDF format is required for a number of NASA-sponsored programs. But in terms of the above project, will Peter be able to answer that? I'm not aware of that. HDF is required.
So like what you say, some of the NASA satellite products, obviously you're familiar with, are required to be produced in HDF. But the science team has not identified a requirement for HDF in investigator-created products. So I would view that as some formats like that would be something that's driven by a science team need. So for instance, I think that Josh Fisher's modeling project is coming up with extensions to the CF conventions, which are built around NetCDF as a file format, but can also sometimes accommodate CSV. So we would have a science team requirement that might emerge from the modeling activities for observational data to be provided in accordance with NetCDF and CF conventions if your data is going to be able to be used as drivers or as verification for modeling efforts. One example I can think of.
Thanks, Peter. So I want to emphasize that NetSDF is a really good format, and it can be used for a number of different sources of the data, including, for example, Ian asked this question, follow-up question, for the airborne remote sensing data. Yes, NetSDF can be a good format for that.
Okay, thank you, Yashing. Okay, and there's a follow-up here. So for the airborne remote sensing data, we can use other formats.
That's right. And ORNL is actually currently dealing with a number of data sets from the NASA programs, from other NASA programs, that they were conducting airborne remote sensing missions, and those data files are in NetSDF format. I want to say that NetSDF is actually a simplified type of HDF, and it provides a lot of useful features, but I would say easier to use than HDF.
Okay, thank you, Yashing. Are there any further questions? If there are no further questions, I would like to thank our speakers today and also Dr. Peter Griffith for providing some input on a couple of the questions here, and thank all of you for participating. All right, fantastic. Thanks, everybody. At this particular point in time, we will log off from the telecon portion. I will leave the virtual meeting space open should you come up with a question, and we will take care of those questions and forward them along. All right, thanks, everybody. Bye-bye now.